The two pillars of modern physics welcome. Pause for a moment. Close your eyes and imagine something extraordinary. Right now, at this very instant, two completely different descriptions of reality are operating simultaneously within the universe. One governs the realm of the infinitely small, where particles dance in probability clouds and exist in multiple states at once. The other rules the realm of the infinitely large, where massive celestial bodies curve the fabric of space itself and move in elegant, predictable orbits. Each of these frameworks has been tested millions of times. Each has proven itself with astonishing precision, yet they refuse to work together. This is not a failure of science, rather, it is one of the deepest mysteries that physics has ever encountered, and it speaks to something profound about the nature of reality itself. Before we begin this journey into the heart of this crisis, I invite you to subscribe to the Relaxing Science channel, give this video a thoughtful like, and share with us where you are in the world and what time it is where you sit right now. Your location and presence matter in this exploration of how space and time themselves remain partially mysterious to us. The story of modern physics is, in many ways, a story of remarkable success. In the early 20th century, humanity witnessed a revolution in how we understand the world. Albert Einstein transformed our comprehension of gravity, space, and time. Simultaneously, quantum mechanics emerged as scientists peered into the atomic realm and discovered that nature operates according to principles that seem to contradict our everyday experience. Light behaves as both a particle and a wave. Electrons exist in superposition, occupying multiple positions simultaneously until observed. Energy comes in discrete packets called quanta, rather than flowing continuously. These discoveries were strange, counterintuitive, and absolutely correct. What makes this situation so fascinating is that both frameworks work brilliantly within their respective domains. Quantum mechanics has enabled the development of semiconductors, lasers, nuclear energy, and the technologies that now form the backbone of modern civilization. When engineers design a transistor, they rely entirely on quantum mechanical principles. When physicists calculate the properties of atoms, molecules, and subatomic particles, quantum mechanics provides answers of staggering accuracy. The predictions match experiments to many decimal places. This is not approximation or guesswork. This is precision science at its finest. General relativity, Einstein's geometric theory of gravity, operates with equal brilliance at larger scales. It describes how the Earth orbits the Sun, how galaxies spiral through space, how light bends around massive objects, and how time itself flows differently depending on gravity's strength. Astronomers use general relativity to predict the positions of distant stars and galaxies with extraordinary accuracy. GPS satellites in orbit require relativistic corrections, or they would accumulate errors within minutes. The theory has been tested in countless ways, from observations of planetary motion to the detection of gravitational waves rippling through space itself. It works. Yet here lies the profound paradox that has troubled physicists for nearly a century. These two pillars of modern physics are fundamentally incompatible. They cannot both be completely correct in the same way that we understand them now. When physicists attempt to combine quantum mechanics and gravity using the standard mathematical techniques that work so well in other contexts, they encounter infinities that refuse to disappear. The calculations become nonsensical. The theory produces predictions that are infinite, which cannot possibly reflect physical reality. This is not a minor technical problem that will be solved with a clever mathematical trick. This incompatibility points to something deeper, something that suggests our current understanding of reality is incomplete. Perhaps space and time are not what we think they are. Perhaps the very foundations upon which we have built our understanding of physics need to be reconsidered. Perhaps there is a deeper layer of reality that we have not yet discovered, one that would reconcile these two great frameworks and reveal them as different facets of a more fundamental truth. The existence of this crisis is, paradoxically, one of the most beautiful aspects of modern science. It represents the frontier of human knowledge. It is the place where our understanding reaches its limits and where future discoveries will be made. Throughout history, the greatest advances in physics have come when scientists encountered contradictions they could not ignore. These contradictions point the way toward revolutionary new insights. The crisis between quantum mechanics and gravity is such a beacon, calling us toward deeper understanding. As we explore this mystery together over the next hours of reflection, we will examine how each framework operates, why they seem incompatible, what happens in the rare situations where both should apply, and what different scientists propose as possible resolutions. We will journey from the subatomic realm to the centers of black holes, from theoretical speculation to the limits of what current experiments can teach us. Along the way, we will discover that this crisis reveals something profound about the nature of science itself, about the limits of human knowledge, and about the beauty of questions that remain unanswered. The universe is far more subtle and complex than any single theory can capture. The fact that we have discovered this incompleteness is itself a triumph of human intellect and curiosity. Let us now begin to understand why these two pillars, each so strong in isolation, cannot yet be reconciled into a unified whole. The quantum realm, a world of probability and uncertainty. Venture with me now into the infinitely small, into a realm where the rules of everyday experience no longer apply, where certainty dissolves into probability and observation itself shapes reality. The quantum realm exists at scales so tiny that they are almost impossible to visualize, yet it is here that the most fundamental processes of nature occur. Atoms are made of nuclei surrounded by electrons. Nuclei are composed of protons and neutrons. These particles themselves are built from even more fundamental entities called quarks and leptons. At every level, as we descend into smaller and smaller scales, quantum mechanics reigns supreme. The foundation of quantum mechanics rests upon a principle that seemed absurd when first proposed, the wave-particle duality. Imagine a single electron traveling through space. In some experiments, it behaves as a particle, as a tiny localized object with a definite position and momentum. In other experiments, the same electron behaves as a wave, spreading out through space, interfering with itself, creating patterns of constructive and destructive interference just like ripples on water. The electron is not somehow switching between two modes. Rather, the very nature of reality at the quantum scale is such that these two seemingly contradictory descriptions are both valid. The electron is neither purely particle nor purely wave, but something more fundamental that displays properties of both depending on how we choose to examine it. This strange duality extends to light as well. For centuries, scientists debated whether light was composed of particles or waves. The answer, as it turned out, is yes to both. Light can be understood as a wave, spreading through space and displaying interference patterns. Yet light also comes in discrete packets of energy called photons, particles of light that carry energy proportional to their frequency. A single photon is the smallest possible amount of light of a given color. When you look at a red laser pointer, the light consists of countless photons, each carrying energy determined by the frequency of red light. This quantization of energy, the fact that energy comes in discrete chunks rather than continuous amounts, is one of the most fundamental discoveries of quantum mechanics. But the mystery deepens when we consider superposition, one of the most counterintuitive principles in all of science. According to quantum mechanics, a particle can exist in multiple states simultaneously until it is measured or observed. An electron orbiting an atom does not have a definite position in space. Rather, it exists in a superposition of many possible positions, described mathematically by a wave function that spreads throughout the region around the nucleus. The electron is somehow present everywhere in this region at once, with different probabilities for finding it in different locations. This is not because we lack information about where the electron really is. This is not merely a limitation of our knowledge. According to the mathematics of quantum mechanics, the electron genuinely does not have a definite position until we measure it. When we perform an experiment to determine the electron's location, something remarkable happens. The wave function, which was spread throughout space, suddenly collapses to a single location. We find the electron in one specific place. Before measurement, there was only probability. After measurement, there is actuality. This is known as the measurement problem or the collapse of the wave function, and it remains one of the deepest puzzles in quantum mechanics. How does measurement cause this collapse? What counts as measurement? Does consciousness play a role in collapsing the wave function? These questions continue to perplex physicists and philosophers alike. The uncertainty principle, formulated by Werner Heisenberg, provides another cornerstone of quantum mechanics. This principle states that certain pairs of properties cannot both be known with perfect precision simultaneously. For example, position and momentum cannot both be specified exactly at the same time. The more precisely we know an electron's position, the less precisely we can know its momentum, and vice versa. This is not a limitation of our measuring instruments or our experimental techniques. It is a fundamental feature of reality itself. It is built into the mathematical structure of quantum mechanics. At the quantum scale, nature itself is uncertain. Despite this uncertainty and strangeness, quantum mechanics makes predictions of extraordinary accuracy. When physicists calculate the energy levels of electrons in atoms, the probabilities of different outcomes in particle collision experiments, or the properties of semiconductors and superconductors, quantum mechanics provides answers that match experimental observations to remarkable precision. In some cases, theoretical predictions and experimental measurements agree to 10 or more decimal places. This level of agreement between theory and observation is almost miraculous. It suggests that despite the strangeness and counterintuitiveness of quantum mechanics, we have captured something profoundly true about how nature operates at small scales. The quantum realm also exhibits a property called entanglement, a phenomenon so strange that even Einstein found it deeply troubling. When two quantum particles become entangled, their properties become correlated in a way that has no classical analog. Measure the spin of one particle, and you instantly know the spin of the other, no matter how far apart they are, even if they are on opposite sides of the universe. Einstein called this spooky action at a distance because it seemed to violate the principle that nothing can travel faster than light. Yet entanglement does not allow faster than light communication, and experiments have repeatedly confirmed that it is a real feature of the quantum world. The quantum realm also includes the concept of quantum tunneling, where particles can pass through barriers that classical physics says should be impenetrable. An electron trapped in a potential well can sometimes appear on the other side of the barrier, even though it does not have enough energy to climb over the top. This is not magic or violation of energy conservation. It is a consequence of the wave nature of matter. The electron's wave function extends slightly beyond the barrier, and there is a probability of finding the electron on the far side. This phenomenon is not merely theoretical. Quantum tunneling is essential for many natural processes, including radioactive decay, and it is also exploited in technologies like tunneling microscopes. Understanding quantum mechanics requires us to abandon our intuitions about how the world should work. At the quantum scale, particles do not follow definite paths. They do not have definite properties until measured. Multiple possibilities coexist in superposition until observation forces reality to choose one outcome. Energy comes in discrete packets. Distant objects can be mysteriously correlated. Yet this strange framework, with all its counterintuitive features, has proven to be the most accurate description of the subatomic world that humanity has ever discovered. It is the foundation upon which modern chemistry, atomic physics, and particle physics rest. General relativity, spacetime as the fabric of gravity. Now let us ascend from the realm of the infinitely small to contemplate the infinitely large. Imagine standing beneath a night sky filled with stars, each one a distant sun surrounded by its own planetary system, each one separated from us by vast gulfs of space and time. The patterns we observe in the heavens, the way planets orbit the sun, the way galaxies rotate and move through the cosmos, all of these phenomena are governed by gravity. For nearly 3 centuries, Newton's law of universal gravitation provided an elegant and accurate description of how gravity operates. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. This simple law could explain the motion of the moon around the Earth, the orbit of the Earth around the sun, and the structure of the solar system. Yet in the early 20th century, Albert Einstein recognized that Newton's description, while remarkably accurate, was incomplete. It failed in certain extreme situations and could not explain some subtle aspects of planetary motion. More fundamentally, Einstein realized that Newton's conception of gravity as a force acting instantaneously across space was incompatible with the principle that nothing can travel faster than light. Einstein's solution was revolutionary and profoundly beautiful. He proposed that gravity is not a force at all, but rather a consequence of the geometry of space-time itself. According to general relativity, space and time are not separate, absolute entities as Newton had assumed. Rather, they are woven together into a single fabric called spacetime. This space-time is not rigid or unchanging. It is dynamic and flexible, capable of being curved and distorted by the presence of mass and energy. Imagine space-time as a vast, smooth rubber sheet stretching infinitely in all directions. When you place a heavy ball on this sheet, it creates a depression, a curvature in the fabric. Smaller objects placed near this depression will naturally roll toward it, not because the heavy ball is pulling them with a force, but because they are following the curved geometry of the space around them. This is Einstein's profound insight into the nature of gravity. Massive objects do not pull on other objects through a mysterious force that acts across empty space. Instead, massive objects warp the geometry of space-time around them, and other objects simply follow the straightest possible paths through this curved space-time. These straightest paths through curved space are called geodesics. A planet orbiting the Sun is not being pulled by a gravitational force. Rather, it is following a geodesic through the curved space-time created by the Sun's mass. The curvature of space-time near a massive object is what we perceive as gravity. This geometric vision of gravity has profound implications. It means that time itself is affected by gravity. In strong gravitational fields, time flows more slowly than in weak fields. A clock on the surface of the Earth ticks slightly more slowly than an identical clock in orbit above the Earth, where gravity is weaker. This is not a theoretical prediction that has never been tested. Atomic clocks placed at different altitudes on Earth show measurable differences in their rates, precisely as general relativity predicts. GPS satellites must account for this effect, or they would accumulate errors and become useless for navigation. Light, which travels in straight lines through flat spacetime, must follow curved paths through curved spacetime created by massive objects. This means that light can be bent by gravity. When light passes near a massive object like the Sun, its path curves slightly. This effect was first observed during a solar eclipse in 1919, when stars near the Sun's edge appeared slightly displaced from their normal positions. The light from these distant stars was bent by the Sun's gravity. This observation provided dramatic confirmation of Einstein's theory and made Einstein an international celebrity. The equations of general relativity, known as Einstein's field equations, describe precisely how mass and energy curve spacetime, and conversely, how the curvature of spacetime determines the motion of objects and the propagation of light. These equations are remarkably elegant, but they are also extraordinarily complex. They involve advanced mathematics and cannot be solved exactly except in special cases. The solutions that physicists have found describe various scenarios: the spacetime around a non-rotating sphere, the spacetime around a rotating sphere, the spacetime of the entire expanding universe, and the spacetime inside and outside a black hole. Black holes are among the most extreme predictions of general relativity. They are regions of spacetime where gravity is so intense that it prevents even light from escaping. At the center of a black hole lies a singularity, a point where the curvature of spacetime becomes infinite and the equations of general relativity break down. Surrounding this singularity is an event horizon, a boundary beyond which nothing can return to the outside universe. Although black holes were initially considered mere mathematical curiosities, astronomers have discovered strong evidence for their existence. Supermassive black holes are believed to lurk at the centers of most galaxies, including our own Milky Way. General relativity also predicts that accelerating masses emit gravitational waves, ripples in the fabric of spacetime itself, that propagate outward at the speed of light. For decades, these gravitational waves remained theoretical predictions. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time coming from the collision of two black holes billions of light years away. This detection provided stunning confirmation of yet another prediction of Einstein's theory and opened an entirely new way of observing the universe. The success of general relativity is almost unparalleled in the history of science. It explains the large-scale structure of the universe, the motion of celestial bodies, the behavior of light in strong gravitational fields, and the very expansion of the universe itself. Yet for all its success, general relativity has a crucial limitation. It is a classical theory, a theory that does not incorporate the principles of quantum mechanics. At the scales and energies accessible to current astronomical observations, this limitation does not matter. But in certain extreme environments, particularly near the singularities at the centers of black holes, or at the moment of the Big Bang, both gravity and quantum effects become important simultaneously. In these regimes, general relativity alone is not sufficient. The scale problem, where two worlds should meet. Let us pause now and contemplate a profound question. At what scale does one framework end and the other begin? Quantum mechanics reigns supreme at the scale of atoms and subatomic particles, typically at distances of billionths of a meter or smaller. General relativity governs the cosmos at the scale of planets, stars and galaxies, at distances of millions of kilometers or more. Between these two regimes lies most of the physical world as we experience it. In this intermediate domain, either framework can be applied, and they generally agree with each other, at least approximately. Gravity is so weak at atomic scales that its effects are utterly negligible. Quantum effects are utterly negligible at the scale of planets and stars. But there exists a special scale, a threshold beyond which this convenient separation breaks down. This scale is called the Planck scale, named after the physicist Max Planck, who, in the early days of quantum mechanics, recognized that a fundamental length scale must exist in nature. The Planck length is extraordinarily small, approximately 1/10 billionth of a trillionth of a meter. At this scale, the quantum nature of gravity becomes important. Both quantum effects and gravitational effects are equally significant. The curvature of spacetime becomes so extreme that quantum fluctuations in the geometry of spacetime itself become relevant. To understand why this scale is so profound, consider what happens as you approach it. In normal conditions, spacetime appears smooth and continuous, like the surface of a still pond. But at the Planck scale, quantum mechanics tells us that spacetime must be seething with quantum fluctuations, constantly bubbling with virtual particles and antiparticles appearing and disappearing. The geometry of spacetime itself must be quantized, divided into discrete units, much as energy and angular momentum are quantized in quantum mechanics. Yet, general relativity, in its current form, does not account for this quantum granularity of spacetime. It treats spacetime as a smooth, continuous manifold. The Planck scale is so impossibly small that we will never directly observe it with any conceivable technology. The most powerful particle accelerators humanity can imagine would need to be larger than the observable universe to achieve the energies necessary to probe the Planck scale directly. Yet the fact that this scale exists, and that both quantum and gravitational effects should be important there, creates a logical necessity. There must be a theory that describes physics at the Planck scale, a theory that incorporates both quantum mechanics and gravity in a unified framework. The situation becomes even more acute when we consider the early universe. According to the Big Bang theory, the universe began in an extraordinarily hot, dense state, compressed to unimaginable density in an infinitesimal volume. In these conditions, the entire universe was essentially at Planck scale. Every point in the universe was a region where both quantum and gravitational effects were dominant. General relativity tells us that space-time itself emerged from the Big Bang. That time has a beginning. But quantum mechanics raises profound questions about what it means for time to begin, about causality, about the nature of initial conditions. These questions have no answer within our current understanding. Similarly, at the center of a black hole lies a singularity where the density becomes infinite and the curvature of space-time becomes infinite. General relativity predicts that at this singularity, the equations of the theory break down completely. The theory becomes unable to describe what happens. Yet, quantum mechanics suggests that at such extreme densities, quantum effects should be crucial. Perhaps quantum fluctuations prevent a true singularity from forming. Perhaps the singularity is replaced by a quantum foam of virtual black holes and white holes, a seething quantum geometry that we cannot yet understand. These are the regimes where the incompleteness of our current physics becomes starkly apparent. We have two magnificent frameworks, each operating perfectly in its own domain, yet each reaching a point where it becomes clear that something more fundamental is needed. The scale problem is not merely a technical issue to be resolved by adding quantum corrections to general relativity or by adding gravitational terms to quantum field theory. Rather, it points to the possibility that our understanding of space and time themselves is incomplete, that at the Planck scale, the very concepts of space and time might need to be reconsidered and reconstructed on a deeper foundation. The Planck scale is so remote from our everyday experience that it might seem merely academic, a curiosity for theoretical physicists, but irrelevant to the real world. Yet this is not so. The early universe operated at Planck scale. The centers of black holes involve Planck scale physics. The quantum fluctuations that seeded the cosmic microwave background radiation, the afterglow of the Big Bang that we observe today, might have involved Planck scale processes. Understanding the Planck scale is essential for understanding the origin and evolution of the universe itself. It is essential for understanding the most extreme objects in the cosmos, black holes that push the boundaries of our theories. The scale problem is not a curiosity. It is a gateway to deeper understanding. The infinity problem, when mathematics breaks down. Imagine a calculation that should yield a finite, meaningful answer, yet when you perform it, using the standard techniques of quantum field theory applied to gravity, you obtain infinity. Not a very large number, but infinity itself, a mathematical quantity that has no physical meaning. Perform the calculation again, using slightly different methods, and you get a different infinity. This is the infinity problem, one of the most fundamental obstacles to unifying quantum mechanics and gravity. In quantum field theory, the framework that has successfully merged quantum mechanics with special relativity for all forces except gravity, certain calculations naturally produce infinities. These infinities arise because the theory allows virtual particles to appear and disappear with arbitrary amounts of energy and momentum. When you sum over all possible virtual particle contributions, the sum often diverges, producing infinite results. However, physicists have developed a technique called renormalization that removes these infinities in a systematic way. The idea is to absorb the infinities into redefined values of the physical constants of the theory, such as mass and charge. After renormalization, the theory produces finite, meaningful predictions that match experiments with extraordinary precision. This renormalization procedure works beautifully for the electromagnetic force, the weak nuclear force, and the strong nuclear force. These three forces are all described by quantum field theories that are renormalizable, meaning that infinities can be systematically removed. The resulting theories make predictions of staggering accuracy. Yet when physicists attempt to apply the same renormalization procedure to gravity, something goes wrong. The infinities that arise in quantum gravity are not of the same type as those in other quantum field theories. No matter how cleverly physicists attempt to renormalize the theory, new infinities keep appearing. The renormalization procedure fails. Why does gravity present this unique difficulty? The answer lies in the nature of the gravitational force and how it couples to all forms of energy and matter. Gravity couples to everything. Every particle, every field, every form of energy gravitates. This universality of gravity means that quantum fluctuations affect gravity in a more profound way than they affect other forces. In quantum electrodynamics, the theory of the electromagnetic force, virtual particles can create virtual electromagnetic fields, and these fields create corrections to the coupling constant of the theory. But these corrections are finite and can be absorbed through renormalization. In quantum gravity, virtual particles can create virtual gravitational fields, which couple back to the virtual particles, which create more virtual fields in an infinite cascade of interactions. Moreover, gravity is described by general relativity, a theory fundamentally based on the geometry of spacetime. Quantizing gravity means quantizing geometry itself, quantizing the very structure of space and time. This is a far more radical step than quantizing the fields that exist within spacetime. It is the difference between rearranging furniture within a room and reconstructing the room itself. The mathematics of quantum geometry is far more subtle and problematic than the mathematics of quantum fields. The infinity problem manifests itself most dramatically in certain calculations. For example, physicists can calculate the probability that two particles interact by exchanging a graviton, the hypothetical quantum of gravity. In quantum electrodynamics, this type of calculation yields a finite result after renormalization. In quantum gravity, the calculation produces infinities that cannot be removed by any standard renormalization procedure. The more precisely physicists try to calculate, the more infinities appear. It is as if the universe is telling us that our approach is fundamentally flawed, that we are asking the wrong questions or using the wrong mathematical framework. The infinity problem is not merely a technical nuisance, a detail to be worked out eventually. It suggests something profound about the structure of reality. Perhaps the infinities are telling us that space and time are not fundamental quantities, but emergent phenomena arising from something more basic. Perhaps the smooth, continuous space-time described by general relativity breaks down at the Planck scale and must be replaced by a discrete quantized structure. Perhaps the very concept of a point in space-time is not valid at quantum scales, and we need a new mathematical framework that does not rely on infinitesimal points and continuous manifolds. The infinity problem also connects to the concept of coupling constants, the parameters that determine the strength of interactions between particles and fields. In quantum electrodynamics, the strength of the electromagnetic interaction is described by the fine structure constant, a dimensionless number approximately equal to 1/137th. This number cannot be calculated from first principles within quantum electrodynamics. It must be measured experimentally. The theory cannot explain why the fine structure constant has this particular value rather than some other value. In quantum gravity, the strength of gravitational interactions is related to the gravitational constant, a quantity that has been measured but never calculated from first principles. Moreover, gravity is extraordinarily weak compared to other forces. The electromagnetic force between two electrons is approximately 10 to the 42nd times stronger than the gravitational force between them. This enormous hierarchy of forces, why gravity is so much weaker than other forces, remains unexplained. Perhaps a unified theory of gravity and quantum mechanics would provide an explanation for this hierarchy. Perhaps it would predict the values of the fundamental constants. These are open questions that drive theoretical physicists forward. The infinity problem stands as a barrier to progress. It prevents us from simply quantizing gravity using the standard techniques that work so well for other forces. It suggests that gravity is fundamentally different from other forces, that it requires new mathematical frameworks and new physical insights. The inability to renormalize quantum gravity is not a failure of physicists to find the right technique. It is a message from the universe that our understanding of gravity and quantum mechanics is incomplete, that something deeper and more fundamental awaits discovery. Information and black holes. The deepest mystery. Consider now the most enigmatic objects in the cosmos. Black holes, those regions of spacetime so extremely curved that nothing, not even light, can escape from within their event horizons. Black holes are places where general relativity's predictions become most extreme, where the geometry of spacetime is most severely warped. They are also places where quantum mechanics must inevitably play a role, for the intense gravitational fields near black holes create conditions where virtual particles should appear and disappear constantly. The intersection of black holes and quantum mechanics reveals the crisis between these two frameworks most starkly. In the early 1970s, physicist Stephen Hawking made a remarkable discovery. He showed that black holes are not truly black. They emit radiation due to quantum effects occurring at the event horizon. The intense gravitational field near the event horizon can separate virtual particle pairs before they annihilate. One particle falls into the black hole while the other escapes to infinity as Hawking radiation. From the perspective of an outside observer, it appears that the black hole is emitting particles and losing mass. Eventually, if Hawking radiation continues unabated, a black hole would evaporate completely, disappearing in a final burst of radiation. This discovery creates a profound paradox, known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed. The quantum state of a system always contains, in principle, all the information about that system's past and future. Yet Hawking radiation appears to be completely random, carrying no information about what fell into the black hole. If the black hole evaporates completely through Hawking radiation, all the information that entered the black hole would apparently be lost forever. This violates a fundamental principle of quantum mechanics. The information paradox is more than a theoretical curiosity. It strikes at the heart of how we understand quantum mechanics itself. If information can be destroyed in black holes, then quantum mechanics as we currently understand it must be incomplete or incorrect. Yet information destruction seems to be what happens when matter falls into a black hole, and the black hole subsequently evaporates. The information about the particles that fell in appears to be irretrievably lost. Physicists have proposed various resolutions to this paradox. Some suggest that the information is not actually lost, but is somehow encoded in subtle correlations in the Hawking radiation that we have not yet learned to decode. Others propose that the information is preserved in remnants of the black hole that survive the evaporation process. Still others suggest that the paradox points to a fundamental revision of quantum mechanics itself, that in the presence of gravity, quantum mechanics must be modified to allow for information loss. None of these proposals has achieved universal acceptance among physicists. The black hole information paradox is intimately connected to the holographic principle, a remarkable conjecture that has emerged from string theory research. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that volume, much as a three-dimensional object can be represented by a two-dimensional hologram. If true, this would mean that three-dimensional space is, in some sense, an illusion, a projection of information stored on a two-dimensional surface. The holographic principle provides a way to think about how information might be preserved in black holes, encoded on the event horizon rather than lost forever. Black holes also reveal another deep connection between gravity and quantum mechanics, the relationship between entropy and area. In thermodynamics, entropy measures the number of microscopic states consistent with a macroscopic description. Entropy is related to disorder, to the number of ways a system can be arranged at the microscopic level. Remarkably, Hawking showed that black holes have entropy proportional to the area of their event horizon, not to their volume. This is a profoundly counterintuitive result. For ordinary objects, entropy is proportional to volume, but for black holes, it is proportional to area. This area-entropy relationship suggests that space itself has a granular structure at the Planck scale. If the entropy of a black hole is proportional to the area of its event horizon, and if entropy counts microscopic states, then the microscopic states of a black hole must be distributed on its surface rather than throughout its volume. This hints that space at the Planck scale is not continuous but discrete, composed of fundamental units. The number of such units within the event horizon of a black hole would be proportional to the area of the horizon. The black hole information paradox and the related puzzles of black hole thermodynamics remain open questions in theoretical physics. They demonstrate that our current understanding of gravity and quantum mechanics is incomplete. They point toward a deeper theory that would resolve these paradoxes and provide a consistent description of quantum processes in strong gravitational fields. Black holes are laboratories where this deeper theory would reveal itself, yet they are also so remote and extreme that we cannot directly test our ideas about them. We can only reason about them theoretically and observe them indirectly through their astrophysical effects. String theory and extra dimensions. One proposed path. Among the various approaches to reconciling quantum mechanics and gravity, string theory stands as perhaps the most developed and extensively studied framework. Rather than viewing particles as point-like objects without internal structure, string theory proposes that the fundamental constituents of reality are tiny strings, objects extended in one spatial dimension. These strings are so incredibly small, approximately the Planck length, that they appear point-like at all scales accessible to current experiments. Yet at the Planck scale itself, their extended nature becomes important. The fundamental idea of string theory is elegant and beautiful. Different vibrational modes of these strings correspond to different particles. A string vibrating in one pattern is an electron. Another vibrational pattern corresponds to a photon. Yet another corresponds to a graviton, the quantum of gravity. By unifying particles as different vibrations of a single underlying object, string theory provides a framework within which gravity and quantum mechanics can be naturally combined. The graviton emerges as a natural part of the theory, not as an awkward addition. However, string theory requires that spacetime have more than the 4 dimensions we experience. In the simplest versions of string theory, spacetime must have 10 dimensions, 4 familiar dimensions of space and time, plus 6 additional spatial dimensions. These extra dimensions must be extremely small, curled up or compactified so tightly that we cannot directly perceive them. A particle traveling through ordinary 3-dimensional space is actually traveling through all 10 dimensions, but its motion through the 6 extra dimensions is so constrained that we do not notice it. The existence of these extra dimensions is not arbitrary. They are required by the mathematical consistency of string theory. When physicists attempt to quantize strings in fewer than 10 dimensions, inconsistencies arise. The mathematics does not work, but in 10 dimensions, the mathematics becomes consistent. It is a remarkable fact that the requirement of mathematical consistency uniquely determines the dimensionality of spacetime in string theory. This suggests that if string theory is correct, the number of dimensions of spacetime is not a free choice, but is determined by fundamental principles. The extra dimensions of string theory are thought to be compactified, rolled up on themselves at scales too small to observe directly. The geometry of these compactified dimensions determines the properties of the particles we observe in our 4-dimensional world. Different geometries of the extra dimensions lead to different patterns of particles and forces. In principle, if we could somehow measure all the properties of particles in our universe, we could infer the geometry of the extra dimensions. Conversely, if we knew the geometry of the extra dimensions, we could predict all the properties of particles. This possibility is tantalizing because it suggests that string theory might explain the fundamental constants of nature, the values of the coupling constants and particle masses that must be measured experimentally in other theories. If the geometry of the extra dimensions determines these constants, then a complete theory of string theory would predict their values from first principles. Unfortunately, the calculations required to extract these predictions are extraordinarily complex, and no one has yet successfully calculated the fundamental constants from string theory in a way that matches all observations. String theory also incorporates supersymmetry, a hypothetical symmetry relating bosons, particles that transmit forces, to fermions, particles that make up matter. According to supersymmetry, for every fermion there is a corresponding boson, and vice versa. This symmetry is not observed in nature at low energies. The particles we observe do not come in such boson-fermion pairs. But supersymmetry might be broken at low energies, hidden from direct observation. At high energies, such as those that existed in the early universe, or that occur at the Planck scale, supersymmetry might be restored. String theory requires supersymmetry to be consistent mathematically, which is one reason physicists believe supersymmetry might be a real feature of nature. Despite its mathematical elegance and the fact that it naturally incorporates gravity, string theory faces significant challenges. First, it is extraordinarily difficult to extract testable predictions from string theory. The calculations are complex, and many aspects of the theory depend on choices that cannot yet be determined from first principles. Second, string theory is not yet complete. There are actually 5 different versions of string theory, and physicists have discovered that these 5 versions are all different limits of a more fundamental theory called M-theory, which itself is not fully understood. Third, string theory has not yet produced any predictions that differ from general relativity or quantum field theory in ways that could be tested with current or foreseeable technology. The difficulty of testing string theory raises a philosophical question about whether it is truly science. Science is based on the principle that theories must make testable predictions. If string theory makes no predictions that differ from existing theories in observable ways, how can it be tested? Some physicists argue that string theory should be evaluated not on its testability, but on its mathematical consistency and elegance. Others argue that the inability to test string theory indicates that it might be pursuing a dead end, and that alternative approaches should be explored more vigorously. Nevertheless, string theory remains the most developed framework for unifying quantum mechanics and gravity that has been proposed. It has attracted thousands of physicists and has generated a vast body of mathematical research. Whether string theory ultimately proves to be correct, partially correct, or fundamentally misguided, the research it has inspired has deepened our understanding of quantum mechanics, general relativity, and the mathematical structures underlying physics. Loop quantum gravity, an alternative geometry. While string theory has dominated much of the theoretical physics landscape, an alternative approach to quantum gravity has developed in parallel, one that takes a fundamentally different perspective on how to reconcile quantum mechanics and gravity. Loop quantum gravity does not introduce extra dimensions or tiny vibrating strings. Instead, it attempts to quantize spacetime itself, to treat the geometry of spacetime as a quantum object, subject to the uncertainty principle and superposition. The key insight of loop quantum gravity is that if we take quantum mechanics seriously and apply it directly to general relativity, we should quantize the gravitational field just as we quantize electromagnetic fields in quantum electrodynamics. The gravitational field is described in general relativity by the metric, the mathematical object that specifies distances and angles in spacetime. If the metric is quantized, then spacetime itself becomes quantized. Distances and angles would not have definite values, but would be subject to quantum uncertainty. In loop quantum gravity, spacetime at the Planck scale is not smooth and continuous, but discrete and granular. Space is built from tiny loops of quantized geometry, each of a size on the order of the Planck length. These loops are woven together to form a network, and this network constitutes space itself. Just as matter is made of atoms, and atoms are made of electrons and nuclei, space is made of these fundamental loops of geometry. This is a radical reimagining of the nature of space. One of the most striking predictions of loop quantum gravity is that volume is quantized. There is a smallest possible unit of volume, smaller than which volume cannot be divided. Space cannot be arbitrarily finely divided into smaller and smaller regions. Instead, there is a fundamental graininess to space, a minimum size below which the concept of space itself breaks down. This quantization of volume is a direct consequence of applying quantum mechanics to the geometry of spacetime. Another prediction of loop quantum gravity concerns singularities. In general relativity, singularities are points where curvature becomes infinite and the theory breaks down. At the center of a black hole, general relativity predicts a singularity. At the beginning of the Big Bang, general relativity predicts a singularity. Yet in loop quantum gravity, singularities are avoided. The quantum nature of geometry prevents curvature from becoming infinite. Instead of a singularity, loop quantum gravity suggests that there might be a quantum bounce, a region where space is extremely curved but finite, where classical space-time transitions to quantum geometry. The mathematical framework of loop quantum gravity is based on new variables for describing gravity, called Ashtekar variables. These variables reformulate general relativity in a way that makes it amenable to quantization using techniques developed in quantum mechanics. The resulting quantum theory is background independent, meaning that it does not assume a fixed background spacetime. Instead, spacetime emerges as a collective phenomenon from the quantum geometry. This is a profound departure from quantum field theory, which assumes a fixed spacetime background on which quantum fields exist. Loop quantum gravity has several advantages over string theory. It does not require extra dimensions. It does not require supersymmetry. It is based directly on general relativity and quantum mechanics, without introducing new fundamental objects like strings. The mathematical framework is more concrete and less speculative than string theory. In principle, loop quantum gravity could be tested by looking for signatures of quantized spacetime at accessible energies, though such tests remain challenging and controversial. However, loop quantum gravity also faces significant challenges. The mathematical formalism is extraordinarily complex, and extracting physical predictions from the theory is difficult. The connection between the quantum geometry, described by loop quantum gravity, and the smooth spacetime we observe at macroscopic scales is not yet fully understood. How does continuous spacetime emerge from discrete quantum geometry? This is a deep question that loop quantum gravity researchers are still working to answer. Furthermore, loop quantum gravity has not yet produced a complete theory of quantum gravity. It has not successfully incorporated all interactions between matter and gravity. It has not provided a satisfactory description of quantum cosmology, the application of quantum mechanics to the universe as a whole. These are not insurmountable obstacles, but they indicate that loop quantum gravity, like string theory, is still very much a work in progress. The existence of multiple approaches to quantum gravity, string theory and loop quantum gravity being the most prominent but not the only ones, reflects the depth of the problem. There is no consensus among physicists about which approach, if any, is on the right track. Different researchers find different frameworks more compelling based on aesthetics, mathematical elegance, and the particular problems each approach seems to solve. This lack of consensus is both a challenge and an opportunity. It means that the field remains open, that new ideas are welcome, and that the ultimate solution might come from an unexpected direction. The experimental silence, why we cannot yet test unification. One of the most frustrating aspects of the quest to unify quantum mechanics and gravity is that we cannot directly test the proposed theories. The Planck scale, where quantum gravity effects become important, is so incredibly small that it lies far beyond the reach of any conceivable technology. Particle accelerators, which are our primary tools for probing the structure of matter and testing quantum mechanical theories, would need to be vastly larger than anything humanity could ever build to achieve energies sufficient to directly probe the Planck scale. The most powerful particle accelerator currently in operation is the Large Hadron Collider near Geneva, Switzerland. This facility accelerates protons to energies of approximately 13 trillion electron volts before colliding them. This is an extraordinarily high energy, yet it is still roughly a trillion times lower than the Planck energy, the energy scale at which quantum gravity becomes important. To directly probe the Planck scale, we would need an accelerator with a circumference larger than the orbit of Earth around the Sun, operating at costs that would consume the entire economic output of the world for centuries. Such an accelerator is not merely difficult to build, it is not merely impractical. It is fundamentally impossible with any conceivable technology based on our current understanding of physics. This absence of direct experimental access to the Planck scale creates a profound epistemological challenge. Science relies on the ability to test theories through experiment. Theories make predictions about how nature should behave in certain conditions, and experiments verify or refute those predictions. But for quantum gravity, we cannot perform such experiments. The conditions where quantum gravity is important are not accessible to us, yet all is not lost. Indirect evidence might point toward the correct theory of quantum gravity. Subtle effects of quantum gravity might manifest at lower energies in ways that can be detected. For example, if space is truly quantized at the Planck scale, this might affect the propagation of light over cosmological distances. Light traveling from distant galaxies might accumulate tiny deviations from perfect straightness due to the granular structure of space. These deviations would be incredibly small, but they might be measurable with sufficiently precise instruments. Some researchers are attempting to detect such effects using observations of gamma-ray bursts and other high-energy cosmic phenomena. Another possibility is that quantum gravity might affect the behavior of black holes in observable ways. The Hawking radiation emitted by black holes should carry signatures of quantum gravity if the theory is correct. By observing black holes and measuring their properties, astronomers might indirectly test quantum gravity theories. However, the black holes we can observe are so far away and so large that they emit Hawking radiation at a rate too slow to detect with current technology. Primordial black holes, small black holes that might have been created in the early universe, would emit stronger Hawking radiation, but we have not yet detected any primordial black holes, despite extensive searches. The early universe provides another window into quantum gravity. The Big Bang represents an extreme condition where quantum gravity effects should have been dominant. The cosmic microwave background radiation, the afterglow of the Big Bang, carries imprints of physical processes in the early universe. Some physicists hope that careful analysis of this radiation might reveal signatures of quantum gravity. However, extracting such signatures from observations is extraordinarily difficult, and the interpretation of any potential signatures remains controversial. The absence of direct experimental tests does not mean that quantum gravity theories are untestable in principle. Rather, it means that testing them requires creativity and ingenuity. Researchers must look for subtle effects that could be detected with current or near-future technology. They must develop new observational techniques and instruments. They must analyze existing data from astronomical observations in new ways, searching for hints of quantum gravity. This experimental silence has also influenced the development of theoretical approaches to quantum gravity. String theory and loop quantum gravity, being fundamentally untestable with current technology, have developed largely as exercises in mathematical consistency and logical coherence. Physicists working on these theories ask what mathematical frameworks are consistent, what structures are forced by the requirement of mathematical self-consistency, and what physical implications follow from these structures. This is a valid approach to theoretical physics, but it is different from the traditional approach of developing theories to explain experimental observations and then testing the predictions. The lack of experimental guidance has meant that progress in quantum gravity research is slower and more uncertain than in other areas of physics where experiments provide constant feedback to theory. It has meant that multiple competing approaches have developed without any clear way to decide between them experimentally. It has meant that some physicists have questioned whether the problems of quantum gravity might be unsolvable in principle, not just with current technology but in any practical sense. Yet the history of science shows that seemingly inaccessible regimes can eventually become accessible through technological advancement and conceptual breakthroughs. The quantum realm was once thought to be fundamentally inaccessible, yet quantum mechanics developed through a combination of theoretical insight and careful experiments at accessible scales. Black holes were once thought to be merely theoretical curiosities, yet we now have strong evidence for their existence. Gravitational waves were predicted in 1916, but not detected until 2015, yet their detection is now routine. The future might bring technologies or observational techniques that allow us to test quantum gravity theories in ways we cannot currently imagine. Philosophical implications. What reality might truly be beyond the equations and the technical challenges? The crisis between quantum mechanics and gravity raises profound philosophical questions about the nature of reality itself. These questions touch on the fundamental concepts of space, time, causality, and the nature of existence. They invite us to reconsider what we mean by the most basic terms we use in describing the physical world. Consider the nature of space. In our everyday experience, space appears to be a container within which objects exist and move. It seems to be three-dimensional, continuous, and infinite. Objects have definite positions in space. Yet quantum mechanics suggests that at small scales, objects do not have definite positions. Electrons do not occupy definite points in space, but exist in superpositions of many possible positions. General relativity suggests that space is not a fixed container, but a dynamic entity that can be curved and warped by the presence of mass and energy. Space is not the stage on which the drama of the universe unfolds. Space is part of the drama itself, If quantum gravity is correct and space is quantized at the Planck scale, then space is not fundamental at all. Space is built from something more basic, from quantum loops of geometry, or from vibrating strings, or from some other structure we have not yet imagined. The three-dimensional space we perceive at macroscopic scales would be an emergent phenomenon arising from a more fundamental quantum structure. Just as the properties of a gas emerge from the collective behavior of trillions of atoms, the properties of space might emerge from the collective behavior of trillions of quantum geometric units. Similarly, consider the nature of time. In our everyday experience, time flows at a constant rate from past to future. Time is one-dimensional. Events occur in a sequence. Causality connects past events to future events. Yet general relativity suggests that time is intimately connected to space, woven together into a single fabric called spacetime. Time flows at different rates depending on gravitational fields and relative velocities. In extreme conditions, the very concept of time becomes ambiguous. In quantum mechanics, the notion of time becomes even more problematic. The Schrödinger equation describes how quantum systems evolve over time, but it does not explain what time is or why it flows in one direction. In quantum gravity, the situation becomes even more subtle. In certain formulations of quantum gravity, time does not appear as a fundamental variable at all. Instead, time emerges as an approximate concept that becomes valid only in certain limits. This is deeply counterintuitive. How can time, which seems so fundamental to our experience of reality, be merely an emergent phenomenon? The holographic principle and related ideas suggest an even more radical possibility, that space and time as we know them are not fundamental at all, but are emergent from a more basic description of reality. Just as a three-dimensional hologram can be encoded on a two-dimensional surface, the three-dimensional space and one-dimensional time we perceive might be encoded in a lower dimensional structure. Reality might be fundamentally two-dimensional, with three-dimensional space and time emerging as projections or illusions. These philosophical implications raise questions about the nature of consciousness and observation. In quantum mechanics, observation plays a special role. The act of measuring a quantum system affects the outcome of the measurement, collapsing the wave function from a superposition of possibilities to a definite result. This has led some physicists and philosophers to suggest that consciousness plays a fundamental role in quantum mechanics, that observation by conscious observers is what causes wave function collapse. However, most physicists argue that this interpretation is not necessary, that any interaction with a quantum system, conscious or not, can cause decoherence and apparent wave function collapse. Yet the role of observation in quantum mechanics remains philosophically puzzling. In what sense does a quantum system have properties before they are measured? Does reality exist in a definite form independent of observation, or does observation create reality? These questions have no clear answers within our current understanding of quantum mechanics. They point to deeper issues that a complete theory of quantum gravity might need to address. The crisis between quantum mechanics and gravity also raises questions about determinism and free will. Classical physics, including Newton's mechanics and Einstein's general relativity, is deterministic. Given the state of the universe at one moment in time, the laws of physics determine the state at any future time. There is no randomness or chance. Yet quantum mechanics is fundamentally probabilistic. The laws of quantum mechanics determine only the probabilities of different outcomes, not the outcomes themselves. This apparent randomness is at the heart of quantum mechanics. A complete theory of quantum gravity might resolve this tension. Perhaps true randomness exists at the quantum level, and the appearance of determinism in classical physics emerges from the averaging of quantum randomness over large numbers of particles. Or perhaps quantum mechanics is not truly random, and the randomness is merely an expression of our ignorance of deeper deterministic laws. Or perhaps the distinction between determinism and randomness is itself a false dichotomy that disappears in a deeper theory. These are open questions that invite philosophical reflection. The beauty in incompleteness. Why this crisis matters. It is tempting to view the incompleteness of our current understanding of physics as a failure, a sign that physicists have not yet solved the problem of unifying quantum mechanics and gravity. Yet there is profound beauty and profound value in incompleteness. The existence of unsolved problems is what drives scientific progress. Without mysteries to explore, science would stagnate. The crisis between quantum mechanics and gravity is not a failure. It is an invitation to deeper understanding. Throughout the history of science, the greatest advances have come from recognizing incompleteness and paradox. In the 19th century, physicists thought they had explained all phenomena through mechanics and thermodynamics. Then the study of light revealed phenomena that could not be explained by classical physics. This apparent incompleteness led to the development of quantum mechanics and special relativity, revolutionary theories that transformed our understanding of the universe. In the early 20th century, physicists thought they had a complete understanding of atomic structure. Then the discovery of the nucleus revealed that atoms had an internal structure far more complex than anyone had imagined. This incompleteness led to the development of nuclear physics and particle physics. The incompleteness of our current physics is a sign of how much more there is to discover. It is a sign that the universe is more subtle, more complex, and more beautiful than we have yet imagined. The fact that two of our most successful theories, quantum mechanics and general relativity, cannot be combined into a single unified framework is not a deficiency of these theories. It is evidence that there is something deeper, something more fundamental, that these theories are approximations of. The quest to resolve the crisis between quantum mechanics and gravity is not merely an academic exercise. The insights gained from this quest have already transformed our understanding of physics and mathematics. String theory has revealed deep connections between quantum mechanics, gravity, and the structure of spacetime. Loop quantum gravity has suggested that spacetime itself is quantized and discrete at the Planck scale. Both approaches have generated new mathematical structures and new ways of thinking about the fundamental nature of reality. Moreover, the pursuit of quantum gravity has practical implications. A complete theory of quantum gravity would help us understand the early universe, the origin of the Big Bang, the nature of black holes, and potentially the ultimate fate of the universe. It might provide answers to some of the deepest questions that humanity has asked. Where did the universe come from? What is the nature of time? Is there a boundary to space and time, or do they extend infinitely? These are not merely abstract philosophical questions. They are questions about the ultimate nature of reality itself. The incompleteness of our understanding also reminds us of the limits of human knowledge. We are finite beings living in an infinite universe. Our brains, evolved to navigate a world of medium-sized objects at modest speeds, are fundamentally limited in their ability to understand the extreme scales and conditions of the universe. The difficulty we encounter in unifying quantum mechanics and gravity might reflect not merely a technical challenge, but a fundamental limit of how much finite beings can understand about an infinite universe. Yet this limitation is not cause for despair. Rather, it is cause for wonder and humility. It is a reminder that we are engaged in a grand adventure, the exploration of the deepest mysteries of existence. Every discovery we make, every theory we develop, every insight we gain brings us slightly closer to understanding the fundamental nature of reality. The journey itself, not the destination, is where the value lies. The incompleteness of our physics also teaches us about the nature of science itself. Science is not a collection of final, absolute truths. Rather, it is a process of developing increasingly accurate and comprehensive descriptions of nature. Each theory is valid within its domain of applicability, but each theory also has limits. Each theory points beyond itself towards something deeper. This view of science as an ongoing process of discovery and refinement is more humble and more honest than a view of science as seeking absolute truth. The beauty in incompleteness lies in the recognition that the universe is endlessly rich and complex, that there is always more to discover, that the human capacity for understanding is not exhausted. The crisis between quantum mechanics and gravity is a beacon calling us toward deeper understanding. It is a sign that the most profound discoveries of the next century of physics lie ahead, waiting to be made by physicists who are willing to question assumptions, to think creatively, and to pursue mysteries with patience and wonder. The journey continues, living with mystery. As we reach the conclusion of this extended meditation on the crisis between quantum mechanics and gravity, we find ourselves not with final answers, but with a deeper appreciation for the profound mysteries that surround us. The universe remains largely unknown, vast territories of understanding yet to be explored. We live at a moment in history when humanity has developed remarkable tools for understanding nature, yet we recognize that these tools are limited, that there is so much more that lies beyond our current grasp. The physicists working on quantum gravity today are engaged in a grand adventure, pursuing questions that touch the very foundations of existence. They are not discouraged by the difficulty of the problems or the impossibility of direct experimentation. Rather, they are energized by the knowledge that they are working on some of the deepest questions that human minds can contemplate. They are seeking to understand the ultimate nature of space, time, matter, and energy. Different physicists pursue different paths toward this understanding. String theorists explore the mathematics of vibrating strings and extra dimensions. Loop quantum gravity researchers investigate the quantization of space-time geometry. Others pursue entirely different approaches, such as causal dynamical triangulation, which models space-time as a network of simplices, or asymptotic safety, which suggests that gravity might be renormalizable at high energies due to a special fixed point in the theory's behavior. This diversity of approaches reflects the complexity of the problem and the recognition that the solution might come from an unexpected direction. The journey toward understanding quantum gravity is also a journey of personal transformation for those engaged in it. It requires developing new ways of thinking, new mathematical frameworks, new conceptual tools. It requires the willingness to question deeply held assumptions and to embrace uncertainty. It requires patience, creativity, and a genuine love of truth and understanding. These are qualities that extend far beyond physics, touching on the deepest aspects of what it means to be human. For those of us who are not professional physicists, the crisis between quantum mechanics and gravity invites us to wonder at the profound mysteries of existence. It invites us to contemplate the nature of space and time, the origins of the universe, the ultimate nature of reality. It reminds us that despite all our technological advances and scientific achievements, we remain humble in the face of the universe's complexity. We are like children standing at the edge of an infinite ocean, having just begun to understand the waves on the shore, while the vast depths remain unknown. Living with mystery is not comfortable. Humans naturally desire answers, certainty, closure. Yet there is also a strange peace that comes from accepting that some questions cannot yet be answered, that some mysteries will not be solved in our lifetimes, that there is vastness and depth to existence that exceeds our comprehension. This acceptance can free us from the anxiety of needing to know everything and allow us to appreciate the beauty of the unknown. The incompleteness of our physics reflects the incompleteness of human knowledge and human understanding. We are finite beings in an infinite universe. We are capable of understanding many things, but not all things. This is not a failure. It is the human condition. It is what makes the pursuit of understanding so valuable. If we knew everything, if all mysteries were solved, if all questions had answers, there would be nothing left to discover, nothing to wonder about, nothing to inspire awe and reverence. The crisis between quantum mechanics and gravity will eventually be resolved. Future physicists will develop a theory that unifies these two frameworks, that explains their apparent incompatibility, that reveals them as different aspects of a deeper truth. When this happens, it will be a momentous achievement, a triumph of human intellect and imagination. But even then, this resolution will likely reveal new mysteries, new questions, new frontiers of understanding waiting to be explored. This is the nature of science. Each answer leads to new questions. Each discovery reveals new horizons. The pursuit of understanding is not a journey toward a final destination, but an infinite journey of exploration and discovery. The crisis between quantum mechanics and gravity is not an obstacle to be overcome, but an invitation to join this grand adventure, to contribute to the collective human effort to understand the universe and our place within it. As you sit with these reflections, as you contemplate the mysteries of space and time, of particles and gravity, of existence itself, know that you are part of this grand adventure. Your curiosity, your sense of wonder, your willingness to think deeply about the profound questions of existence, these are all contributions to the human quest for understanding. The journey continues, the mysteries remain, and in that mystery lies the infinite potential for discovery and growth. I'd like to know, where are you listening from and what time is it there as you contemplate these cosmic mysteries? Your presence and attention matter. Thank you for joining me on this journey through the deepest questions of physics. If this experience has brought you a sense of wonder and inner peace, I would appreciate a like and subscription to Relaxing Science. Also, please let us know if you would like to see more content exploring the mysteries of physics, consciousness, and existence. The universe awaits our understanding, and together we continue the eternal journey of discovery. Total.